start
All right.
recording. We're
Very good.
live.
Hello.
So hello, Daniel.
Hello.
We were just having a quick discussion about what we are going to cover today, which is matrices. So what I was going to say was, once you get once you have like the matrix class, like I mean this X and A, it's like matrix dot create, I don't know, translation, vector, or what is it, like 3 2 1 whatever, and so on. Like you just have the method, and it's like, oh, I've got matrix A and B, and I'd be like, matrix C equals A times B, and like once you have that all down, you sort of stop having to think about the maths behind it. Anyway, so which is why like I had to go and have a quick brush up on my own maths here, because it's helpful to know it, but it's sort of stuff you don't really practice that much in the end.
Right.
So let's just have a quick go at the whiteboard, and that's if we can find what happened to it. There it is. Okay, so let's see. Okay, so as we were saying, I'm not sure I mentioned it since I hit record, but so we've been watching this bring it over here, this Essence of Linear Algebra series from 3 Blue 1 Brown, which is pretty good. So chapters 3 and 4, which is like they're the linear transformation matrices, is sort of what we're going to be focusing on, because that's what you want to do in games. So basically you have let's see, you have a vector v, and it's like, all right, I want the vector v times matrix A equals v dash, which is a new vector, and we'll call those vectors to notate them nicely so we know they're vectors. So if let's say we have some axes, and the vector v goes off here, and let's say that A happens to be a rotation matrix through 90 degrees. So what will happen is, actually I'll use red for this one.
Is the dash a matrix too?
No,
The A and the dash? Okay.
So A is a matrix, and the other two are vectors. So vector times matrix equals vector. So if A is a rotation matrix through 90 degrees, you'll get this business here. So that should all be fairly familiar about how these matrices work. So are you with me so far?
Barely. I mean, I get it. But yeah, I don't know if I actually watched chapter 4. Chapter 3, I think was the part where I threw my hands up in the air, ran screaming from the TV.
That's okay.
But I'm pretty sure. Yeah, I mean, I understand how I intuitively can visualize the translation, affecting the result of that vector. But
so let's have another matrix like B. So if this one was, a rotation matrix, we'll call B like a B equals V dash, and we'll call this one a scale matrix. And so maybe if it's that's our original vector, and if it's just a scale matrix like 2 times scale,
it's just going to be like almost like an underline,
it'll be up like that. But let's say let's just make sure we know which one is which. Let's have V times C, which can be a scale like I think I'll say equals kind of q dash. And we'll say that is a scale matrix with x times 2 and y times 1, for example. And we'll make that one blue. So this one here.
Yeah, isn't that the one you just did? That's blue because it's the y.
Okay, so let me do this. So this one's like x scale times 2 and y scale times 2. So this one is
don't.
I'm forgetting the name for this. A uniform scale matrix, I want to say. Like it scales uniformly on both axes, whereas this one is scales differently. So that one is going to scale 2 times on x. So it's like this is the x-axis here, so there, and so 2 will come out to there, whereas y-axis goes up to there and it scales times 1. So maybe that one, this q here, will go out to there. So with a different matrix we get a different result. And let's say matrix v equals vd equals qr. I don't know why I'm dashing these ones, but let's call that one a scale matrix with scale x times 2 and y times 3, and then we'll go like, all right, 2 we already know it's going to be out there, and y 3, 1, 2.
How is this different than just multiplying another vector, like the 2, 3 vector? Isn't it?
So, how is it different to just multiplying the components? Well, in this case, it's not. It's actually pretty much, we'll multiply the x component by 2 and we'll multiply the y component by 1. So that case is actually fairly simple, and I'll show you why once we get into the numbers. So then we could say, let's have another matrix, and we'll call this a skew matrix. And so perhaps what we'll have is, let's say that's our vector. In fact, let's say our vector is this time. And a skew matrix, it will do basically like this to our vector if it's skewing it by that distance there on the x-axis. And so if perhaps we had a different vector, this one, it will tend to skew out. Well, it won't tend to skew out. Like this particular matrix might skew it out to there.
Right.
Whereas if we had, say, this vector, that vector stays the same. So the result of applying a skew matrix is this exact same point there. So it sort of shifts along a single axis. So that's sort of some interesting things you can do. I'm just going to have a look.
Right, that's because you're treating everything at the origin, right? That's why we're getting.
Exactly.
That's why you didn't just move the red arrow like across the lines. I remember that part, sort of.
Yeah. So what we will get into, and so this is an interesting case, and that is, for the time being, we're going to ignore translation. So, we'll leave this out for just a bit because we might not get to that till next lesson, because this one's a bit different. So if you have like a vector out here, a translation would be like, let's add that to it and get, this vector here. And a translation matrix would be like, well, and we might also have this vector here. And, if we add that to it, that same sort of green dotted one, we get like this vector here. And if you if you consider these as like, I say this is like I haven't drawn this brilliantly for this, but like say this is a model, like maybe it's like a nice thick line with a stick on it or something, and we translate it, we end up with the same nice thick line with a stick on it or something, and it's just moved a bit. Mm-hmm. And so anyway, and you can treat this like, this is still able to be treated as a matrix, but this one is actually a bit more complicated. So we'll get into that sort of after we do these other ones. But the interesting thing is that you can combine these, and you'll have hopefully have seen these. Like if you have, matrix A times matrix B, you get a matrix C that is the combination of these two transformations. So you could, for example, combine a translation and a scale, and you might end up being like, well, here's my world, and it's like, actually, let's say here's my game world, and say this is the origin here, and if we were to say, right, let's render that to a screen, that doesn't look very useful for like a gameplay, for gameplay, because you've got like, your little dudes like tiny down there, and so we want to like scale the game world up, and we want to move the camera so it's pointing here. So what we do is we apply a scaling matrix and a translation matrix, and maybe if we're doing some special effects, we might also do like a rotation matrix to like wobble the screen or something, and you'd end up with it's scaled up and it's being translated, because there's the rest of it, and the origin's off down there somewhere, like off the end of the page. So do you understand how that works?
Yeah, it almost, I don't know what the term for the property of that is, but when you combine multiple things sort of, idempotently without any like side effects from the previous one, that are safely combined, sort of like when you do that with forces, D'Alembert's law or whatever that is, where you can like take a bunch like of friction and force and like smash them together, and they don't they don't result in things you don't expect, I guess. Is there a property name for that? Because I think you're kind of describing that sort of like how you can have a string of matrices, and you can figure out what they're going to do. Like they're not going to.
It sounds like you're mixing up like two different things.
Sure.
Well, maybe three things if you count physics, but I kind of get what you're saying. So the thing about matrices is, first of all, they can be combined. So, like, and
they're independent.
They're,
in a way.
They are independent. And
does order matter though? That's the thing.
Order does matter, and so maybe I'll show you that next. And I would encourage you to maybe rewatch the 3 blue 1 brown videos after this, because unlike me, like it takes me a really long time to like animate something in this.
Yeah, exactly.
And he's like,
I'll watch it right after.
He's like, whoop, whoop, oh look, it does that. So there's a couple of things. First of all, is the idea that they are linear. So like there's no matrix you can do like no linear transformation matrix that you can use that would like end up making, you know, transforming your stick with a thing sticking out of it into like a curve perhaps or something. Like that's never going to happen.
Right.
And even if we were scaling, like
yeah, I remember the video doing all those cool patterns when it does skew.
If we were if we were rotating, like here's our happy little smiley face, and we rotated that through 90 degrees, you know, that would happen. And you could, like, if you had a scaling matrix, like, you know, if that's the situation there, you know, it would get bigger. There's no situation where, and you know, you could do this. Like, you could squish it down like that, but there's no situation where you're going to end up, you know, with like this sort of business.
What's a convolution filter then? Isn't that?
That is something completely different.
Okay.
And it's a little bit outside my knowledge range. I believe it's something that you apply to bitmaps.
Okay. For some reason, I had that idea in my head about making that curvy thing, because you have to convolute the shape of it. But that's, yeah, it doesn't matter.
I think
that's just good for.
I think that's different. I think when you do a convolution filter, there is a matrix involved, but it's not something I've done, so I don't know the maths off the top of my head for that. So that's sort of a rough idea of what matrices can do. And I'm just had a thing up. List. Okay, like, yeah, stretch, rotation, shear, reflection. Oh yeah. So reflection should be fairly obvious. It's like scale, but with, like, you know, y equals -1, for example. And that will, you know, so in that case, maybe, you know, you'd end up with like that. Okay, so let's talk about some numbers, because that's let me just sort out a new layer. This is the fun bit. So what we're going to do just for today is 2 by 2 matrices. And so now there's a tricky bit here, and that is if we have, let's say the vector v equals x, y, and the matrix A equals A, B, C, no, actually, equals A, B, C, D. You know, and then we get v dash equals x, y, each of them dashed. You know, we get v times A equals v dash, which, you know, then we get x, y times A, B, C, D equals, and we'll do the maths for that in a sec. There's another way of doing this, and so this is a row vector, and what you'll find in like a lot of maths focused stuff, and like, so this one tends to be used by like DirectX or Direct3D and the like, and sort of seems to be common for, I guess, 3D graphics and stuff. But mathematicians tend to do it like a v equals v dash, and then v equals x, y, a equals a, b, c, d, but these are actually different because it's kind of like transformed, which means that it's, I'm doing this from memory, I think it's, yeah, a, b, c, d, if like you would never write it like that, and you wouldn't put that in. You just accept the fact. I think that the A and the B are different, but in this case, like this, all these A, B, C, and D, if I write it like that, they are identical to this A, B, C, D. Hopefully that made sense.
Sort of.
So it's basically different ways of writing it, and then you've got V dash will be X dash Y dash, which means that your matrix thingy will be A, and now I'm gonna switch notation, so just ignore all of that now, because now these A, B, C, and D are different to the above. So
okay.
A, B, C, D times X, Y equals X dash Y dash. So,
right.
So this is what you'll tend to see when you're looking at like maths focused I guess material, including the 3 blue 1 brown videos.
Yeah, it seems easier to read than the other one.
Okay. Well, I'm just thinking maybe we'll use this notation and switch when we need to implement something. And then this one tends to be what you find, like this is, there is no 2x2 matrix in like X and A. I'm not sure. I don't think there's one in direct 3D.
Yeah, that's what I've been wondering this whole time, is how that maps, because I've never seen a matrix 2D.
So we will get to that, because that's quite interesting how that works. And basically, it's what lets us do translation.
Mm-hmm.
Whereas with only a 2x2 and in 2D, we can only do the first couple of things. We can do rotation, scale, skew. So this notation here. So how about let's start working with this notation here. And we'll try and convert it. It depends. What do you feel most comfortable with? Like, do you want to do the notation conversion step later after we've done all the maths, or do you want to?
Yeah, I'm fine with using the other one.
The more
graphicsy one.
The graphicsy one.
Yeah.
All right, let's work with the graphicsy one. And so this is mainly just be aware of this. When it comes to watching like other things, so we'll completely ignore that ourselves for now.
Okay. Yeah, the ABCD thing. AB was it?
Oh, okay. Yeah. Those are pretty much arbitrary.
Right.
So we have a 2x2 matrix A, let's say, and let's start with what's called the identity matrix. So in fact, we won't call it A, we'll call it I, which is conventional. So if we have a vector V times the matrix I equals the vector V.
Right.
No dash.
This part I know.
So, okay, so if you know this part, it should be fairly straightforward. I'm already drawing column vectors. So this is like X, Y times the identity matrix, which is 1, 0, 0, 1 equals X, Y. And so what's happened here? Let's talk about how we actually do this multiplication.
Right.
So let's flip back to ABCD. So X, Y times A, B, C, D. And this is kind of the annoying part, because like you never need to do this by hand. And when I say never, you occasionally need to do it by hand if you're doing fancy things. But
right.
And when you're like making your initial sort of matrix I say class, but like struct or whatever. You have to sort of, you have to know this occasionally, but it's, this is the sort of thing you can look up on Wikipedia when you actually need to know it, and obviously you need to make sure you're using the right, row versus column, as we're talking about. So the way this works is we have a 2 by let's have a look at, so here's the Wikipedia article on matrix multiplication, because like even I don't remember how all this works, but basically the way that it goes is you take the first matrix, which in this case is a vector, and you go across, and you take the second matrix and you go down. So we know that the result is going to be a 1 by 2 matrix, and the way that we know that is is 1 by 2 and 2 by 2, and you take that one, and I think yeah, so if you look at the Wikipedia article on matrix multiplication, it just says that.
Okay. It's just, do that. Do these rules. Okay,
so so we know that this is also 1 by 2, and so let's try and get rid of that because we're going to need more space. So what we do is we go across and we go down. So the first spot, we'll take this one and this one,
mm-hmm.
and so that's x times a, and then we take this one and this one, so that's plus y times c, and that's our first element in our 1 by 2 matrix, which is our vector. Then on the next one we take, we're going across still here, and we're going down still, but we're now in the second column, so it's first row, second column. So this is first row, second column, and we're going to take x times b, so xb plus y times d, so and then we yd. So that is the very simple way to do matrix multiplication. So, and what you find is if you use this identity matrix, if you do all that multiplication, c is 0, so c is 0, so that's 0, so that cancels out, and b is 0, so that cancels out, and then a is 1 and d is 1, and so you find that what's left is,
you didn't have to do any work at all, because chopped it up.
Yeah, so it's x and y, so you're back where you started. So we can build on this and make scaling matrices, because so what you should have noticed there is, if I go back a couple of steps, is if a and d were different values, like if a were 2 and d was 2, then I get x2 and y2. So hopefully you can sort of see that then is, that's scaled up by 2. Does that make sense?
Yeah.
Yes?
Sure.
So, and one way of looking at that, and you'll see this in the video, is you take your basis vectors. So this is like x hat, and this is y hat, and if you scale them up, you get, and they call it, what is it? Like this, if that's twice as, if x hat is twice as big, and call it I hat. So, and that's twice as big with j hat, you end up, the x vector scale at 2, the y vector scale at 2. But what you can do is if you have like this vector here, and I have to draw this quite carefully. There's x, and then that's y, and let's say that's our vector there. Actually, I'll go a bit smaller. Let's say our vector's here. So it's, what you find is it's 1 on x and 2 on y. So it's, it's the vector 1, 2 is that one. Now, if you change the basis vectors and you scale it up, so we scale that one by 2 and we scale the y by 2 as well, it's now going to be 2 of j hat. So we'll have 1 and then we'll have 2, and 2 of I hat, sorry, 1 of I hat, because 1x. So just have one of those, and you end up with this vector here that's been scaled up 2 times. By the same token, if we have the matrix, let's get scribbly. Now we're going to scale x up by 3. So then all of a sudden I hat is not 2x, it's now going to be 1, so it's 1, 2, 3 times 3 times our x-axis basis vector. You end up going out to here, and you get this vector here. And so what this is this 1, 2 vector, and it's made up of 1 times I hat and 2 times j hat. So we've basically just stuck this I hat and j hat in. Now what's interesting about I hat and j hat is I hat is, and I have to be really careful to get this right, I hat is this vector here, and j hat is this vector here. So you'll notice that j hat is 0 on the x and 2 on the y, so it's up there, whereas x hat is 3 on the x-axis and 0 on the y. But what you can do, which is interesting, is you can shove these basis vectors anywhere. So if we go like this, we can say, let's say with 45-degree rotation, so we have x is there and y is there. Actually, I'll draw those a wee bit bigger so we can get a good look at this. If x is there and y is there.
These are I and j hat, right? And not x and y anymore.
So what we're going to do now is, and I'll hue shift a bit. We're going to rotate 45 degrees. So that's going to be I hat, and this is going to be j hat. So which is equivalent to rotating x and y through 45 degrees. So what you find is if we do this maneuver here, so if I and j is the transform, what happens is we're going to take we had 1 of I, and we had 2 of j. So let's start with 2 of j because that's easier. We'll go 1 on j, 2 on j. We end up here, and then we'll add on 1 of I. We end up here. So that's this vector here. Whereas before, we just had 1 of x and 1, 2 of y. We had, this was our original vector there.
Right.
And so what you find, of course, and hopefully all of that made sense, is that is 45 degrees.
Well, it would be, okay, it's just not in real, it's not when you drew it, but it is 45.
Yeah, that's, ignore the poor drawing, but so it's, suffice to say that rotation through 45 degrees is the same as that rotation through 45 degrees is the same as that rotation through 45. And that's the other interesting thing, like as I was saying before, it linear transformation matrices move space linearly, I guess. And so like if you rotate that through 45 degrees there, you have a point here, it rotates through 45 degrees there. It doesn't sort of rotate up there and sort of create this sort of weird skew-if shape from a circle or something. So following me so far?
Yeah. I held on for that one.
All right, so let's look at, okay, so as I was saying, these are vectors, and in theory they're the same as the basis vectors. So what we should find is if we do a rotation through 45 degrees for each of these, it should cause our actual vector to rotate. So let's make a new layer and try and break that down. And let's hope I got the maths right, because as I was saying, it's making sure you get your rows and your columns the right way around is helpful. Okay, so we had x and y, and we had a, b, c, d, and then equals x dash y dash. Okay, so what we were just doing is we had the vector to 1, and we had, that was our x and that was our y, and now we want to rotate this. And just to make our lives easy, we're not going to do, we're also sort of going to scale it as well, just to make that was wrong. Y is there because that's like 2y. Okay, so what we're going to do is we're going to see what happens if we want to take that and we want to go up here, and we want to go up there. Oops, sorry. And so I'm just going to call that 1, and I'm going to call, that 1. If you recall from, when we were talking about trigonometry and stuff, like if we start at 1 here and we draw the unit circle, like we've, just for the ease of calculation, we've actually made these slightly longer than the unit circle. So it's not a pure rotation, it's also scaled up a bit, just to make the maths easy. So are you following me so far?
Yeah, other than you put the 1 there, I think I got my direction wrong because I thought that was -1 on the red.
Yeah, sorry.
Oh, it is? Oh.
Yeah, that's -1. You're quite right.
Okay,
that's +1. On the x-axis, ignore the color of those numbers because they're...
Yeah, that's fine.
Not...
Okay.
Okay, so what we're going to do, let's make a prediction about what our basis vector is going to be, and we'll see if I have my columns and matrices right. I think I do. So our x-axis, it was in the identity matrix 1, 0. Now we're going to make it, what, 1, 1. So 1 on the x-axis, 1 on the y-axis. And the y-axis, when we rotate it, it was going to be 0, 1 for the identity matrix. But now we're going to make it -1 on the x-axis, and we're going to make it +1 on the y-axis. So this is going to be our rotation and slightly scaled matrix. So let's see what happens when we take the vector, which we had here.
How's it slightly scaled if all the values of the matrix are ones?
Because you'll notice that our basis vector has got longer. So if you remember, the length of a vector is the square root of 1 times 1, so x times x, x squared, plus y squared, which is 1 times 1, which is the square root of 2, which is 1.4, blah, 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 blah. So the length has changed from 1 to 1.4.
Sure.
So if we were scaling up a bit, we would do...
You just arbitrarily decided that, right? I mean, we're trying to derive the matrix that got us there.
So we're trying to...
We started on the left, and we're trying to get to the right.
Yeah, we started with that, and we want to do this, and we're just deciding that this is what we're going to do. And we're only doing this. We're not doing like the same thing, but with like that length there, and like that length there, just because that's easy. Because otherwise, instead of 1, -1, it's going to be
right. That's a bunch of stupid.
We have to normalize it with like square root of 2, square root of 2.
Okay. Oh yeah. So you're just describing the fact that if we plug the ones into all of these, because of how length of the vector works, we're going to get a little bit extra. That's all you're describing, right?
Yeah, and I mean,
just to keep the math simple.
Just to keep the math simple. And if you're in the mood, we can like stick that factor in there. Stick that factor in the mood. Okay. So,
yeah, and if we did, we'd have a nice clean one inside the circle. All right, good to go.
So let's finish that off geometrically, I guess. So what we were saying is we have 1 on the x-axis and that on the y-axis. So we're going to have 1 there, and we're going to have 2 of these. So we go out, there's 1, and we'll come out 2, and we end up there. So we should get that vector out at the end. And what you'll notice is it's not only rotated by 45 degrees, it's also scaled by 1.4, blah, blah, blah. Even though these diagrams aren't exactly to scale, but you sort of should get that impression. Okay, so let's hope that is correct, because otherwise I'll have to go and fix it. I'm pretty sure that's right. So let's.
Where did you decide where did you decide that the blue arrow was going to be 1 and 2? You just made it up.
I just made that up. So that's going to be 1, 2. So the point is that will work for anything. So if we're stuck, say, that vector into there, it would become, it would be like -1y, and it would end up out there.
Makes sense.
Okay, so let's do this. Let's do this maths here, down here. So we had the matrix, the vector 1, 2, and we had the matrix 1, 1, neg 1, 1, neg 1, 1, and so equals. Now we know that it's going to be a 1 by 2 matrix, so it's like we'll take the we're going across and down, so we're going to take the first row and the first column to get our one position. So 1 times 1 plus 2 times -1. So 1 times 1 plus 2 times -1. Now we're going to do the next column. So that's 1 times 1 times 1 plus 2 times 1, so that one times that one. 2 times 1 gives us 1 times 1 is 1, plus 2 times -1 is -1, I think. And 1 times 1 is 1, plus 2 times 1 is 3. Do I have that maths right? 2 times 1 is 2 plus 1, so it's 3. Cool. All right. So let's see if we got that right. -1, 3. And that, we're looking pretty good here. So
yeah, you can see it. So
-1, and then 1, 2, 3. We're up. We're up there.
Yeah.
So that is how that works. Now, let's sort of finish up by saying, let's finish this section up by thinking about exactly what we were talking about before. I think it's probably the most useful thing. So this is where we go back a little bit to that stuff we were doing on trigonometry. So we know that if we have a unit circle and we go 45 degrees, we know that that is going to be length 1. And it's going to be, and we know that if we travel out 1 unit on each axis, we end up here. And so we have 1 divided by square root of 2, which equals 1 divided by 1.4, which equals, well, we can sort of calculate what that equals, because we know that if this is our unit circle and that's theta and that's 45 degrees, we know that that is the cos, I believe. Yeah. So that distance there is cos theta. And we also know that this distance there is, so that distance on the y-axis is sine theta. And what we can do is we can basically, as we adjust theta, we can more or less just rotate vectors around the unit circle. So for theta 0, we have x equals 1 and y equals 0, which should, x is 1 and y is 0. If we have a theta of 90, we have x is 0 and y is 1. And so what we know from this, because we know the way that cos works around the unit circle, we know that to get this situation, we need something like, we know that there's going to be a cos, there's going to be a sine, and cos, because we know that we know that to get this, basically our sort of identity basis vectors, we need something like this, but we're missing a sign here that we have to figure out. And you'll notice I'm having a little bit of trouble explaining this one, because this is exactly the sort of thing that you write once and forget about. So if we wanted to rotate, so as we were doing before, if we want to rotate through 45 degrees and end up with that there, we have to take our x-axis and it needs to be positive and positive. So, this was positive on x-axis and 0 on the y-axis, like positive 0, and this was 0 and positive. We know that the result is going to be positive and positive, and we know the result here is going to be negative and positive. And so what we know then, we derive that is the matrix that we need to use. But you had
that was out of band information. Right? You figured that out because you plotted it on the basis vector, right?
What I've done there is I've derived what those basis vectors are going to be geometrically. So it's exactly the same result as if I'd gone and looked on Wikipedia what a rotation matrix is. But hopefully you can see there that that's a basis.
But we're not saying it's always. We're not saying that it's always negative. We're saying that it's negative in this case.
Yeah. So what we're saying is to get this result out of a 45-degree rotation, and as well to get this result out of a 0-degree rotation. So that's like theta equals 0, theta equals 45. To get those results, the only way you can do it is using the sine and cos as to derive these vectors on the unit circle, and the sines and stuff have to be this way around. And also, if there's another way to derive this, if you remember, we had the perp 90 function, and what you could do is you could take your because we know that this is perpendicular in this particular space, and it's perpendicular in this particular space. Like there's no skewing or anything going on. We can say that the y equals perp 90 of the x, which means that j hat equals perp 90 of x hat. And you'll have to forgive me for messing up the colors, but sorry, not x hat.
You mean I hat.
Right? I do mean I hat. Of I hat. And what you find then is if you say perp 90 of cos theta sine theta, you remember that our perp 90 function was just perp.
Right. Yep.
You remember that basically if you apply the perp 90 function, it's like negative of the y-axis is the x-axis.
Yeah.
So it's like negative
y
sine, positive x.
Yeah, that's right.
Cos theta. So there's like three.
Kind of relates to
three. Sorry.
I said I like sometimes when the math clicks together, even though it might not make sense to me intuitively. It's right there. But it all kind of lines up.
So there's three different ways to derive the rotation matrix, like geometrically and using perp 90, and they all sort of work together, and you get this matrix here. And furthermore, what you find with this, and I guess it is kind of like, to a certain extent, you have to take it on faith, I guess. And that is like, if you want a rotation matrix for like, I don't know, however many, is that 135 degrees? No, however many degrees that is. It's exactly the same. This works for any value of theta.
So we can derive a matrix that would provide an arbitrary angle of rotation.
So this,
clockwise.
So this entire thing is the definition of a rotation matrix.
Oh. In one direction, right?
Yes, yes. So as we were saying when we were talking about the trigonometry,
right, counterclockwise is default.
Yeah, if y plus goes up, then it's counterclockwise. But and this will become relevant when we implement this thing. If y plus is down, then the rotations theta will go that way.
Right.
For exactly the same reasons as it's always been. So at this point, it should be sort of getting quite like sort of mentally nice. It's like, theta is, this sort of links like how I guess trigonometry and matrices work, and this concept that rotation starts at 0 on the x-axis and goes around to the positive y-axis no matter which way up it is, and keeps going round, should start to get really comfortable at this point, I guess.
Mm-hmm.
Okay, so that is sort of that. Are you comfortable now with, we have transformation matrices, we have identity matrix, we have scale, and we have rotation.
Identity, scale, rotation, yeah. We didn't do translation, but
we haven't done.
You said it was a little harder.
It's a little. It's actually almost. It's probably not that much harder, but it is a little bit different. Let's say. So we've left that out for now.
We don't have to cover it now. But this is anecdotally with our CRU, how the drawing system takes great pains to remember that it's flipped the other way, right? It's different than direct. It's different than XNA wants it to be in terms of positive y's and results.
There's
in movement upward.
There is a flipping stage because when we draw stuff, it's got to be this way up.
That's right.
Because that's the way that Sprite Batch works, and we happen to be using Sprite Batch. But when we simulate stuff, pretty much everything is in this form. So there is a stage at during the drawing where this flip takes place, and that's written in such a way that doesn't really hurt us. Like it's been put in the pipeline in the position where it's pretty much seamless. Like you don't really notice it. Basically because sprites have an awareness of their origin and stuff. So, when you go to draw it, it puts the sprite at the right spot.
Well, you say it's seamless, but I mean it's only after you've gone through the mental, like maybe you've been using XNA forever and you're used to the Y down, then you switch to the other way. It makes sense after you realize that everything's the opposite way.
Yeah.
You have to think about it in the opposite. But it's probably for people who are actually mathematically or geometrically inclined, it's probably like easier to think, oh good, I'm in the same uprightness that I want to be in.
Yeah, this like working in this space is just like after doing a lot of games, you just find that this is just so much easier mentally, and then at some point you have to do this flipping business, and you just do that.
Is that only in XNA, or is that open or other engines and stuff are on the left?
It's actually arbitrary, and so XNA arbitrarily picked this one because it makes a little bit of sense because that's what Windows does. But like
client coordinates.
Yeah. So you could conceivably write, my sprite batch, which just always uses those coordinates, and it spits out, triangles in that way to draw the sprites and so on. And I've tossed around the idea of doing it but this is also is probably a bit easier just to write the flipping logic at the right spot in the engine, depending on what you're doing.
Yeah, that's interesting.
Okay,
but I mean, you wouldn't get any noticeable performance benefit of doing a nice sprite batch, or
It's for sprites, no, like because there's there's 2 triangles per sprite, so.
Right. Yeah, just a spot where you draw stuff on top of it.
Yeah, like if you're doing because that's the other one that we didn't really say. If scale is the same thing as mirror, so it's if you have a scale anywhere in your system, it's just like, well, we just negate the y-axis at some point to do that flip. And you have to like make sure, because the thing is, if you do it naively, if you have that is your sprite and there's the origin, and you just flip it, you end up with that, or vice versa. That, which is obviously not what you want, because then your guy is upside down. So there is.
Yeah, just remember. Yeah.
This is like flipping it. Obviously, is completely trivial, but this
it's not the result of a mirror that you want. Yeah, especially
this situation. Yeah. So the way that we handle that to a certain extent is we don't really like when this side of the physics and stuff queries like, oh, how big is my sprite? It's like, oh, it's that big. And it's like, what's my alpha mask? Oh, it's this business in this space. And when the drawing system says, oh, I want to draw now, it's like, okay, give me an origin. The origin, as you can see, is exactly the same point. And give me the sprite, and the sprite is in this space. So the sprite is actually that, and so it draws exactly what you'd expect. So that's sort of how we do the flip, is we make sure the sprite and the screen are both in this space, but all the data about the sprite, including like the width, the height, the alpha mask and stuff, is in this space.
Right.
Okay. So.
Yeah. Interesting.
Now, how are we on time? We're actually running a wee bit.
We're past, yeah.
We're running a wee bit later than I wanted to go. So, how are you feeling? Are you in the mood for a small amount of programming?
Yeah. Okay.
Let's
do it.
Let's bring up the editor, and because what I want to do is I want to basically implement. I want to implement this. And I'm not sure how long this is going to take, so maybe we'll just talk about what this involves. Maybe this can be homework.
Yeah, because you were saying, I mean, we don't have Matrix 2D, so it's going to be a little bit of maneuvering in here, right, to make something that's useful.
Yeah, so let's just come down to the bottom or something, and let's say struct, and I know this is like an interior. What is it? It's like a inner class or something. So let's say matrix 2D. Let's call it that. And float A, B, C, D. Or, so this is one way we could do it. This is the other way. This is the other common notation.
Yeah, I've seen that before.
I kind of prefer this one, just because it makes it clear. Like, you remember we talked about over here. There's like, we can have A, B, C, D, or we can have A, B, C, D, depending on whether you what way around it is and whether you've transposed it or anything, and that just makes life a little bit complicated. And whereas if you put that one, it's like always. That's always. I'm about to say that's always, and it's like that's always row. I think that's always row. Yeah, that's always row, and that's always column.
Right.
That. And
I'm surprised that we're making a struct. I mean, I don't think we have a matrix 2D, and the game. Like maybe because we barely had to do any translation or scale or anything like that because it was all very much one-to-one.
Yeah, I can't. Well, I don't want to bring up the source code on stream, but I can't remember. I think I think we did have some kind of transformation matrix, but it was maybe a bit specialized.
Yeah, probably. I just don't recall. I know we don't have that primitive, let's say.
Yeah, certainly the thing that I'm thinking of was barely used. And yeah, actually no, with the camera system and stuff, like even though it's only 2D and does only this plus the translation stuff that we're going to talk about, we use the full, XNA matrix, which is because we're FNA, we can actually bring out the source code. Represents a right-handed 4x4 floating point matrix, blah blah blah, and you see it's like public fields. So M11, they're not counting from 0.
They're one based, yeah.
Yeah, maybe we can copy them. So anyway, so let's just make this struct for now.
Ugh, 1 Yeah, okay. I like your explain before, by the way. That's good. We'll use the way people do it.
So you like which way?
I like the 0, 1.
Yeah, well, we can do that if you like. Are you in Visual Studio? Is your screen sharing still going?
Yeah.
Okay.
Oh, you want me to follow?
Yeah, follow along. Because
it's just I got a clicky keyboard. So
no, that's alright. Well, so do I. So, let's think about what we can do with this. We can have static matrix 2. Whoops, that's not good. Static matrix 2D public static matrix 2D create rotation. So we can just copy what we had before and float. Actually, we'll call it float's fine. Call it double because we're going to use the maths stuff. And so this is something that we can just copy from here. So we have sine and we have cos of theta. So float sine equals maths float maths dot sine of theta, and we can have cosine. And I mean this is just sort of banging it out. So m, what have I done here? Yeah, you float m0 0, m01, m10, m11. Okay, so we can say m00 equals what was it? It's cos m11. M01 equals sine. M10 equals negative sine, and M11 equals cos. So, hang on. That's static, so...
I have to make a new instance. Yeah.
Ta-da! So, and I'll just bring up the thing. So yeah, cos, sine, neg, sine, cos. Cos, sine, neg, sine, cos. Looks good to me.
All right.
So that was really straightforward. So and then the other thing we can do is public vector 2 vector 2v. So what do we know about this? So this one is this is exactly what we had on here. I've kind of scribbled over it, but it's let's figure this one out. So
m0 0 times the x plus m0 was left to right, step down, so this would be m1 0 times the y.
Going left and going down.
Yeah, that's going down. Yeah, 0 0 and then 1 0.
So
and then the other one would. Oh wait, no, wait.
Yeah, you spotted it, I think.
Sorry,
so row is the first number, column is the second number. So you're correct, and I'm wrong.
Well, we're done. That's all I ever needed was that to happen once. Okay. All right, so then okay, so yeah, and then the rest is 0 1 times x plus m 1 minus.
Hang on, it's like. So this is why this is complicated. So what I'm going to do is it's a little trick that I find helps a bit, is to make sure that's the right way around. There's also a consideration of what order you put these in memory. Just if you're like passing, if you're passing one of these into like a native thing that expects a pointer to like a series of floating point numbers that's in a particular order, you need to make sure the order matches. So if you're like passing this into OpenGL, for example, or DirectX, you need to make sure these match. Anyway, now I'm thinking about it. So row 0, 1.
I think they're the same. I just flipped my orders to different orders for M and B.
Yeah. Let's stick with that for now, and if we're wrong about it,
yeah, this is down, and this is down.
Yeah.
Yeah, we're good.
Okay. Yep. So this is the part where it's like, am I matching what the math says? Have I labeled everything correctly? And if you haven't, this is what testing is for.
I think you've got it. I think we're good.
Okay. So, this is, and we may as well just, while we're here, copy, create rotation, and create scale, and
scalar. Yes. Oh. All right. Yeah, because it's 2 components. Sure.
So that should be x 0.
I thought floating point was bad. We should be using ints. I guess you can't really do that for this. No. Actual angles.
Yeah. No. So I have made integer-based matrices before. There's one in the old XN project, and it was actually stored. It actually stored a is it called a rational? Yeah, I think it's like a numerator divided by a denominator as integers, and it used that for like pixel-based transformations for like Windows and stuff.
We have that in Pixel 3D. There's a fraction class with a numerator and denominator.
Yeah.
Use it for ballistics and stuff.
Yep, it was similar to that. Okay, so we've got our happy little matrix 2D class. So and hopefully haven't made any maths errors in there. I think you're right. I think it is correct. So what we could do with this is, for example, we could make we have this nice line method. So we could say copy this and add on add on a transformation and be like start equals transform times transform.transform start. and end equals transform.transform end. So get rid of that for now. So that was our line from the other day. And let's make it a bit more.
Hold on, I gotta.
That's all right. Let's see if this works. Let's.
Gonna make another one and then. What is this monstrosity?
Well, maybe change the colors so we can see it. Create rotation, just a smidgen of rotation, and 0.7f. Okay. Okay. So let's see what you've got there. So our code should pretty much match. So, and we get the same result. So now recall that this is all based up in the top left-hand corner is the origin. So when we scale this point by 1.5, it ends up there. If we scale this point by 1.5, it ends up there. If we rotate these points, this one and this one, by however many radians that was, I tried for a small amount so it would stay on screen. It rotates clockwise because we're in this client space with y positive pointing down.
Right.
And so it looks like everything's working. And we can go in here and maybe we can be like, well, let's scale that by a little bit. Why has that stopped working? Where are we?
Edit and continue to update?
Yeah, no, I'm in release build rather than debug for some reason. Yeah, so we could like scale that by 2 and scale that by 0.25, and we could rotate that by maybe less, and and we get that. And so this has been scaled a bit up on the on the y-axis, but doubled on the x-axis. So it's like I can't point to my monitor and show this, but like x is coming out to here, and then x is coming out to here, so it's like double. So, and then our rotation has gotten smaller, and that looks pretty good. So hopefully you're happy with that. We managed an implementation there that's not too shabby. So what I will do, yeah, I think I'll leave it there. So as I was saying, we can now take what we want to be able to do in the end is be like matrix 2D foo equals that times that, and implement
do both things.
Yeah, and then we could just use like foo in there and apply like a scale and then a rotation. But
right, we're just missing the implicit operators, which I can add. I'll add them to my code.
Yeah, I mean, like
for homework or whatever.
There's as I was saying, I mean, I don't really want to go into this because we are over time.
No, that's fine.
Too much detail, but like as we're saying, if we have the matrix A, B, C, D, and the matrix A, B, C, D, E, F, G, H, you can do the same process and you get a 2 times 2 matrix, and it's like, for this one here, well, you take, what did I say? It was a crossing down. So we take these two
and then
these two, and then for like, this one you take, we're still on the top row, so we take that and we take F and H, and if we did that one, we take the bottom row and that one and so on. So hopefully like that process that we did still works. So if you're really keen, you can just go ahead and implement that. So yeah, but
yeah, that seems. Well, I mean, that should be easy with implicit operator overload or whatever it's called.
Yeah.
So yeah, that's good.
Yeah. Well, I'll tell you what, we'll make that the homework. So I'll leave you to have a crack at that, and I'll link like the Wikipedia article on matrix multiplication for anyone watching along. It's fairly straightforward. So yeah, we should be pretty happy with that. So I guess next week, if we haven't got up to
I'll have to do the other stuff.
Yeah. Well, I'll tell you what, next week if we haven't got up to doing that multiplication, we'll do that. But we'll also talk about how to do a translation matrix and sort of the ins and outs of that. So let's finish off. Where's my button? Here's my button. All right. Okay, and